let's unpack this challenge. We are diving into solving a 13th degree polynomial today.
Which is quite the task.
Right. I mean, in high school, you maybe solve quadratics degree 2.
Yeah.
But mathematicians know once you get past degree 4, classical algebra kind of, well, throws up its hand.
It basically says, I give up. Yeah. And that's actually formalized, isn't it?
It is, by Abel's impossibility theorem.
Right. Which states that for polynomials degree 5 or higher, you generally can't express the solutions using just, basic arithmetic, adding, subtracting, multiplying, dividing, and radicals. Roots.
Just hit a wall.
Exactly. For about 200 years, the only real way around that wall was just settling for numerical approximation.
And settling isn't just mathematicians being picky, is it? You mentioned approximation can be a real problem.
Oh, absolutely. In fields that need extreme accuracy, it's a huge liability, actually.
How so?
Well, approximation inherently introduces fuzziness. You get rounding errors. You lose that absolute perfect precision you need for complex scientific models.
Like modeling black holes or designing a bridge.
Precisely. Anything where tiny errors can compound, you need precision that holds up, maybe over billions of calculations. Approximation just doesn't cut it sometimes.
Okay, so the classical tools are limited by the radical thing, and numerical solutions aren't precise enough. Where does that leave us?
Well, that brings us to our main topic today, Professor Mourad Sultan Ezouidi's theorem.
Right. And the claim is this method creates a whole new way, a symbolic structure, to get exact solutions, not just estimates.
That's the core idea. It claims to bypass the restrictions of Abel's theorem. It's not saying Abel was wrong.
Okay, important distinction.
Very important. Abel was right about solutions using radicals. Ezouidi's work basically says if you step outside those classical constraints, you can build a different kind of systematic process.
A structured symbolic process.
Exactly. To derive the roots perfectly. It suggests the limitation wasn't maybe inherent to the equation itself, but more about the algebraic language we were trying to use.
Hmm. So wait, if the old definition of solving meant expressing roots and radicals, and Ezouidi's solution isn't necessarily in that form, is he essentially redefining what it means to solve a polynomial?
That's a great way to put it. He's proposing a new systematic pattern or procedure.
Okay.
If you can define a root perfectly, symbolically, and crucially, prove it satisfies the original equation, then you've found an exact solution.
Regardless of whether it looks like a traditional square root formula.
Exactly. It's more about the process proving the truth, not just the final formula fitting the old world.
Interesting. Let's talk about the specific polynomial he tackled. It wasn't simple, was it?
No, not at all. It was a dense, full 13th degree polynomial, 14 terms, big coefficients.
Starts with 60 size, ends with a constant term. $17 million. You probably shouldn't be able to pronounce it that long.
Probably not. But yeah, it's a great test case because it's got, maximum potential for complexity built in.
And the source material pointed out something interesting early on.
Yes, a rather curious detail. For this specific polynomial, C wheeling 1 is actually a root with multiplicity 5.
Multiplicity 5. For our listeners, what does that mean in practice?
It means if you were to factor the polynomial completely, the terms sucking and dumbing would show up 5 times. Like $899 times 7 times.
Okay, so that hints that this polynomial isn't just random numbers. It has some structure.
Definitely. It suggests a specific, maybe even constructive nature that Ezouidi's method could exploit. But the real challenge and the breakthrough is finding all 13 roots using the theorem.
Right, including the ones that aren't not simple integers like 1.
Exactly.
What's fascinating here is how the method works. You said it's systematic, structured, recursive, not guesswork.
That's right. Think of it maybe like a mathematical filtration system.
Okay.
The goal isn't to jam the existing coefficients into some radical formula that Abel said won't work. The goal is to systematically re-engineer the polynomial structure itself by calculating a sequence of new values. The paper uses specific notation, but we can think of them as SRAR, where it goes from 0 up to 12 for this 13th degree case.
And these scryal values, they become the new coefficients.
Exactly. They represent the polynomial in this new structured format, and the calculation is recursive, meaning to find, say, the value for $60, you need the values you already calculated for $17,000, $73, and so on. It's a step-by-step process.
Ah, okay. So it's not like a single magic formula, but more like an assembly line, systematically taking apart the complexity.
That's a good way to think about it, yeah. An assembly line or a filter. The calculations themselves rely heavily on things like binomial coefficients.
Like from Pascal's triangle.
Exactly those. They help adjust terms and manage the interactions between the different powers of x. This whole recursive application of structure, it acts almost like a systematic error correction.
But instead of correcting numerical errors, it's correcting or simplifying the algebraic complexity.
Precisely. It's designed to transform that initial messy polynomial, the one that's effectively unsolvable classically, into a much simpler, sparser form.
A form that is solvable.
Right. It's essentially changing the mathematical language the problem is written.
Okay, because the complexity usually comes from all those terms interacting, right? All 14 coefficients in the original equation.
Yes. And Ezouidi's recursive method is designed to systematically account for and sort of filter out those interactions. Ideally, it leaves behind only the core, structurally important coefficients.
So they applied this big recursive process, 13 steps, to this huge polynomial. Now, logically, you'd think the results, these new saw coefficients, would be even messier numbers, wouldn't it?
That's the intuitive assumption, absolutely. If we were just brute forcing calculations, the numbers could get astronomically complex.
But that's...
You know, some math problems are so tough, we basically filed them away in a drawer labeled impossible. But what if someone found a key to unlock one of them? Today, we're going to dive into a pretty bold claim, a new way to solve an equation that has stumped some of the greatest minds for centuries. Just take a look at this thing. It's a 13th degree polynomial. For centuries, finding the exact values for x to make this equation work was considered, well, pretty much impossible. Something you could only get close to. This isn't just an equation, it's a mathematical monster. So that raises the question, what if unsolvable is just a temporary label? The source material we're looking at today presents a method that claims it can do the impossible. Slay this mathematical dragon and find the exact treasure hidden inside. Alright, so here's our game plan. First, we're going to see exactly why this kind of problem was such a fortress for so long. Then, we'll check out the new key that claims to open it. We'll watch it work its magic, and then see what kind of answers it gives us. And finally, we'll ask, what could this mean for science? Okay, let's get into it. So picture this. For a long time, mathematicians were on a roll. They figured out these neat formulas for second, third, even fourth degree polynomials. But then, bam, they hit a wall, a big one. At the fifth degree, the magic ran out. They discovered there's no universal formula for getting a perfect answer for equations like this one. And that's been a basic rule of the game ever since. But then, Professor Mourad Sultan Ezouidi comes along with a claim that really shakes things up. He's basically taking on a mathematical giant, Abel's impossibility theorem, which is this huge foundational idea that says there's just no general formula for these kinds of problems. And he's saying, yeah, I think I found a way around that. And this really breaks it down perfectly. Think about it like you're an archer. For hundreds of years, the best we could do is get our arrows really close to the bullseye. That's approximation. But Ezouidi's theorem, it's claiming to be the arrow that hits dead center every single time. No more close enough. So, what exactly is this new mathematical key? Let's take a closer look at how it's supposed to work. Okay, so at its core, think of it like a translator for math. It takes that super complex, frankly terrifying original equation, and then step by step, it rewrites it into a much, much simpler language, a language we can actually solve. All right, now for the fun part. We're going to see this theorem in action. We're going to unleash it on that monster equation we saw earlier. And don't worry, we're not going to get bogged down in the complex calculations. We're just going to watch the magic happen. So the process is what's called recursive. It's basically a chain reaction. The theorem does one calculation and then uses that result to kick off the next one, which kicks off the next one, and so on, creating this incredible cascade of simplification. And right away, things get really, really interesting. The first 5 new coefficients in calculus, they all come out to 0. It's like the equation is just shedding its own complexity piece by piece. And then, bam, the 5th one is different. It's not 0. It's this massive but very specific number, 13 to the power of 6. It's like we just found the first piece of the hidden treasure. But after that one big number, the pattern comes right back. The next 5 5 calculations, all 0 again. The equation is getting meaner and meaner. And then, just when you think it's all zeros from here on out, we get one more. The 11th coefficient is another huge, super precise number. So think about that. Out of 13 new numbers, only 2 actually survive. Everything else just vanished. Okay, so we're left with just 2 important numbers. What does that all mean? Well, this is the payoff. This is where those 2 numbers unlock the whole thing. Because almost all those new coefficients turned into zeros. That huge, intimidating polynomial we started with just collapses. All the complicated bits just fade away. And this is what's left. I mean, look at that. The mathematical monster has been completely tamed. It's been transformed into something, well, something we can actually solve. It's just an incredible transformation. And from this simplified form, we get our answers. One of them is obvious, right? X equals 0. The other 12 are found by solving that smaller part inside parentheses, which is now a way easier puzzle. And the key thing here, these aren't just close guesses. They are the exact, symbolic, crystal clear solutions.
So, okay, this is incredible from a pure math perspective. It's beautiful, right? But what does it mean for the real world? Why does getting a perfect answer matter so much?
Well, think about it. In fields like quantum mechanics or high-level engineering, even the tiniest rounding error can have massive consequences. It's kind of like building a skyscraper, but your foundation is off by just a fraction of an inch. By the time you get to the top floor, that tiny mistake is a huge, dangerous problem. Exact solutions mean a solid foundation. And the really exciting part is, this isn't just a party trick for one specific equation. The claim is that this method could be a master key, able to unlock any of these high-degree polynomials. It could be a total game changer, moving us away from good enough approximations to perfect, exact answers. So it really makes you wonder, right? If a problem that was considered impossible for centuries can suddenly be solved, what other mathematical walls are just waiting to be climbed? What other impossible problems are maybe not so impossible after all?
Hello, Mr. Mourad. How are you doing? We start with things okay with you. Okay, I just saw your message. Okay, thank you. Okay. Thank you, Mr. Alhamdulillah. Already, let's say, so I have seen your message. Thank you for this one. Thank you.